All right, let's start. Hello, everyone. This is Dr. Yuzo. This is our ECE 360 control system class, and today is our 18th lecture. And first of all, can you guys hear me well? How about screen? All right, thank you, guys. All right, let's move forward. No question? All right, let's move on. Last lecture, we studied the rule locus further by trying to decide if any randomly given point on the rule locus or not. Basically, the points along the rule locus is once again are the closed loop transfer function poles. And also, they all follow two properties. Right? They all follow two properties. One is called magnitude property. Second is called phase angle property. So the points along the rule locus always follow these two properties. And by utilizing which, we are able to find or say judge if the given point is along the rule locus or not. Okay. Let's take a rough look at these two properties in details. First, the magnitude property is meaning KGH. First of all, who is the KGH? You need to understand KGH means nothing but our open loop transfer function. Okay, they're referring to such block diagram of system. Forward transfer function G, feedback H, and by introducing a gain K, they're able to vary it from 0 to infinity, so we have a rule locus. So in the property, magnitude property, that's the KGH means nothing but the open loop transfer function. The magnitude of it equals to 1. Second, the phase property means still KGH, the open loop transfer function. The phase angle of it is what? It's basically odd number times of 180 degree. Be careful, it could be positive or negative. Okay, in other words, positive 180 and the negative 180, they're the same angle because they have 360 degree as difference. So they're exactly same angle. Okay. These are the two properties. Using which we start to solve the problem. First problem, example 1, given the point, a specified point. Check if this is on the rule locus. And if it is, we can find the corresponding K value. If not, obviously, we should ignore the question too, right? So how to judge this? We are using the phase property to judge. Okay. And remember this, use the phase property to judge. Use phase property to check. So first of all, we need to find the open loop transfer function. This guy is KGH. It's in terms of S, obviously. So by the given system block diagram, we can tell the KGH is equals to the K times S plus 3 times S plus 4 divided by 1 S plus 1 and times S plus 2. Right? So this is our KGH, and based on this KGH, we start to use the phase property. So the phase angle of this transfer function is equals to what? Angle of K, which is constant, it's the introduced constant gain, plus the angle of S plus 3 plus angle of S plus 4, minus angle of plus 1, minus angle of S plus 2. Okay. So here is what's the math background behind this is, assuming you have a phasor, you have phasor A magnitude angle B times C angle D, divided by EF times G angle H. Assuming you have such operation among four different phasors, because if you substitute S here by complex number, then this is nothing but a bunch of phasors, or say complex number, right? So how to conduct the math here? What is it? In terms of the magnitude, is just as simple as A times C divided by E times G. Does it make sense? This is the operation among phasors. The result is also phasor, with magnitude of AC divided by EG, with a certain angle, right? What is the angle then? Angle just equals to angle B plus angle D minus angle F and then minus angle H. Does it make sense? This is the math. This is the math behind. Following the same idea here. Okay, that's why we have the first result line. Yeah, this is the first line here. And what's next? It's just a substitute S by given point value. And then you are looking for the phase angle for each complex number. It's a calculator job. It's a calculator's job. Like, just make sure your calculator is functioning. And then we end up with 90-180. 90-180, as I said, it's nothing but a positive 180, the same angle. Therefore, the conclusion is the given point is on the Locus. It's on the Locus. So the answer to question 1 here is yes. Is yes. Therefore, we have to solve the k value correspondingly. How do we find the k value? To find k value, we need the magnitude property. Okay, we need magnitude property to find k value. Okay. How to do this? Once again, we already have the open loop transfer function kgh, and we know kgh magnitude. Okay, once again, magnitude and magnitude only is equals to magnitude of this guy the mathematically, just like what we reviewed here, just the equals to what? K value. Because K is a positive constant. K is positive constant. Equals to S plus 4 magnitude divided by the magnitude of S plus 1 times magnitude of S plus 2, right? And once again, we substitute S value by the given -2 plus square root of 2 divided by 2j. Okay. Substitute S value. And then just the algebra. Yeah, just the algebra. You should end up with this. This is nothing but the algebra. Okay. You plug in the S value and then go to a calculator to find the magnitude value. Once again, magnitude. So you end up here. And this equals to what? Equals to what? Equals to 1. Remember, that's the property. Therefore, from here, we are seeing one equation, including only one unknown, which is k. So find k value here. It's 1/3. Just as simple as this. As simple as this. Using, once again, phase property to check a given point. Second, use the magnitude property to find the k value. If the given point is along the Locus. Any questions for this problem? All right, if this is okay, then let me ask a couple of extra questions. Try to clarify the concept even better. Let me ask a third question. Let's say, what is the closed loop transfer function when k equals to 1? What is the closed loop transfer function when k equals to 1? This is a very straightforward, right? So k equals 1 means your system k equals to 1. Your g of s remains as this. And your h of s equals to unity. Okay. That remains same. That remains same. The closed loop transfer function, you just look from here. Right? Look from here. What is it? One plus g h s. Okay. And of course, here we know we have k here. We know we have k here. But both k's are 1, right? Both k are 1. And then we got whatever is supposed to be turned out to be this. Of course, here I'm flip the denominator in the denominator into the numerator. That's why you are seeing this. You are seeing this. Nothing special. And the algorithm, or say this block diagram algorithm, we learned from a previous module. So you need to understand when k equals to 1 along the rule locus, the points at where k equals to 1 corresponding to what? Closed loop poles of the original closed loop transfer function without introducing k value. To the original system transfer function without, or say before introducing the k value. The next question. What is the closed loop transfer function? Let's say just the denominator polynomial. We don't have to find the numerator. We just find the denominator. When k equals to 1/3. How to know this? How to know this? Well, we need to recall the previous question 2 result. We are seeing when k equals 1/3, what is the point we are talking about along the rule locus? Which 2 points? Or which point we're talking about? Is exactly the given point, right? That makes sense. Which is when k equals to 1/3, rule locus points is -2 plus j. Because of the question 2 answer, substitute this particular point into the magnitude property, you're finding the 1/3, right? So going back, if k equals 1/3, then what is the Locus point we are talking about? Is this point. However, complex pose, of course, closed loop pose. This point is nothing but closed loop pose. Remember, because we are talking about a point along the rule locus. Of course, is the closed loop pose. We know one is this. We definitely know the other, right? Or say the complex pose appear in a conjugate pair. Does it make sense? So if one point is this, we definitely have another point, which is -2 minus square root 2 divided by 2j. So now these two are what? -2 plus and the minus square root 2 divided by 2j are two closed loop poles at k equals to 1/3. Right, this is the conclusion we can have. Take a look to see if it makes sense. Okay, this is the conclusion we receive based on actually the question 2 answer. Any questions? All right, if this is fine, then once again, these are two closed loop poles. Two closed loop poles. And then we can find the corresponding what? Closed loop denominator polynomial is what? S minus one of the poles times S minus the other pole. Of course, we are talking about polynomial, so it should give equals 0. Does this make sense? And further, if you organize it, you should end up with s squared plus 4s plus 4.5 equals 0. This is how we find out the closed loop denominator polynomial at a particular k-value. Because at this particular k-value, we are able to find two poles. Yeah, two poles. Two poles are meaning nothing but the closed loop denominator polynomial roots. So we have two roots, and then we find the polynomial equation. Right. Does this idea make sense? Any questions? If all right, well, thank you, Kevin. If this is fine, then of course we actually have another way to find the closed loop denominator polynomial, right? Well, that another way might be easier. However, it's not as helpful as the first idea here to better understand the rule locus. Okay? The easier way, I think. Well, since we know the closed loop transfer function as this, right, as here. So if we just substitute k value by 1/3, we're finding the closed loop transfer function directly, right? From there, you can, of course, find the closed loop transfer function denominator polynomial. Of course, you can. But remember, this second idea is based on a fact that the system block diagram is given. In other words, if the system block diagram is not given, you must be able to, first of all, understand how you come up with these 2 points. Second, how these 2 points can compose a polynomial. This is how you link, how you understand the rule locus. Because if I give you the rule locus, okay, without giving you any block diagram, without giving you any transfer function, based on the rule locus, can you locate the point and understand the point is closed loop poles? And from the closed loop poles, can you find the closed loop denominator polynomial back? Does it make sense, this logic? Okay, that's the kind of in-depth understanding of the rule locus. If you from here directly substitute k value by 1/3, of course you can add everything, right? Everything you want. But if this is not given, okay, this is not given, how you find the polynomial? Here, this is the idea. Okay, so here, of course, it equals to 1/3. Go to the kg divided by 1 times kgh. You can find everything you want. Transfer function, denominator polynomial. All right, any questions regarding this example? All right, if no questions, we can move on to example 2. A similar problem is very straightforward. Given a block diagram like this, we are checking another given point, -3. It's on the rule locus. And if it is, find the corresponding k value. The idea remains same. First, find the kgh, which is the open loop transfer function, right? From which we go ahead to apply the phase property to check the given point -3 is on rule locus or not. Right? If it is, then use the magnitude property to find the k value. Of course, if the answer for this second step checking here is no, then we can just ignore the third step. Right? So this is the idea, the procedure. So if no questions, please go ahead, try this problem yourself by 5 minutes. Then I will present the solution. All right, go ahead. 5 minutes from now on. And by the way, during conducting the problem, if you have any questions, you can pop up right away. Okay, I'm listening. Here, yeah, that is reaching a 0 degree as the phase angle of the KGH, and is 0 degree indicating the point on the rule locus or not on the rule locus. First of all, of course, we are not discussing whether the 0 is the correct answer or not. Okay, we are not discussing that yet. But if you're assuming we are reaching the 0 degree, what's the conclusion? Anyone know? Speak. Come on.
It means it's not on the RL, right?
Correct. Okay, that's the correct answer from Sawyer. 0 degree is obviously not the odd number times of 180 degree. So if 0 degree is the answer, then that means it is not on rule locus. Okay, it's not. All right, let's see this problem together. So it's a pretty much exercise of the calculator, in my opinion. First, the KGH equals to this, right? Oh, no. Right, this is the KGH, open loop transfer function, and based on which the angle of this KGH is equals to angle of K plus angle of S plus 2 minus angle of X squared plus S plus 13, right? And if you calculate the angle, you find very straightforward, right? You're seeing positive 180 as the answer. Of course, positive 180 is also equals to negative 180, and they're the same angle. So the answer is yes, it is on the rule locus, right? This is on the rule locus. So all of these angles here are actually the angles are of constant value. That's the phase angle. So yes, magnitude property, and the magnitude of this guy is equals to K times S plus 2. Magnitude of S squared plus 4 squared 4S plus 13 is equals to K times 1 divided by 10. This equals to 1. That's the magnitude property. And then from where you can find the K value here, just equals to 10, right? Does everything make sense? Any questions? Any questions? Now, how I got 180 degree here? You mean here? You mean this guy?
Yes.
Your S plus 2, because your S plus 2 equals to negative 1, right? And negative 1, what is the phase angle? 180.
Oh.
Positive value constants is 0, remember?
Right.
This is what I discussed here. Last lecture, if you recall that. Positive value is a vector towards right. towards the positive half axis of the x-axis. Value is towards left, right? Along the negative half axis of the x-axis, right? Negative half. So this is their angle respectively equals to 0 and 180. And also purely imaginary number also follow the same idea along the y-axis. One is positive, another is negative. Say 2j. What is the angle of 2j? What is the angle of negative 2j? I mean, what is it?
Is it negative 90?
Negative 90. Here we go. Or is also equals to what? Positive 270, right? This is how we tell the purely real number, positive or negative, and the purely imaginary number, positive or negative. So here it should be very easy thing. It should be very straightforward thing. And for the same reason, we have k here is angle 0, and one angle of 180 or 90, 180. It doesn't matter. Any other questions? It's not difficult, but in the exam, just calm down little by little. Don't make minor mistakes. Right? It should be fine. Should be fine. Okay, let's just spend very little amount of time to do one more example. Try to make this perfect. Check if point, this time the point given is -2 plus 3j on the Locus of example 1 system. And if yes, then find the k value. And you just need 3 minutes. Go back to example 1. I'm here presenting example 1 system. How about that? Check a different point for the same system of example 1 to tell what is the phase angle this time, right? You just need to tell the phase angle. And after this example, I think it's time for us to really talk about how to really sketch the rule locus. Okay. Go ahead. Any degree value? Any phase? Anyone got? $180. No, for this different point, no, it is not 180. Any other phase angle we received here? Hey, here we go. Noah is right. Okay, Noah got negative 70 degree. Yep, it is negative 70 degree. And basically, we can have here the phase property KGH, because we already got the KGH from example 1. So here equals to this part remains same. And constant K and phase angle 0. S plus 3 phase angle, we just substitute this value here, right? And then what is the angle for it? 71.56. Same thing, 56.31 degree minus 108.33 degree minus 90 degree. And then the result is negative 70.56 degree. No. Right. Therefore, we are able to ignore the K value. We should ignore the K value. Let's take a look. I think once again, just to make sure your calculator is functioning well. Okay? And that's the key, I'm afraid. Any questions? All right, if this is fine, then we go ahead and really sketch a rule locus. And we start to really sketch rule locus. How to sketch the rule locus? We talked about it just a very, very little, tiny bit. And therefore, I'm providing a much more detailed procedure here. As one of our handouts available in the Canvas module, you should be able to download it even before the class. But if not, that's fine. Okay, just remember to print it out as your future handout. Okay. So I'm providing a procedure. And the Roman number 1 and 2 here, you're seeing 2 sections. So 2 sections. First section is how to plot the rule locus on the real axis, or say how to deal with a transfer function, including only real axis, open loop poles, and open loop zeros. Section 2 is dealing with the transfer function who has open loop complex poles and complex zeros. One thing you need to remember, we always use an open loop transfer function to plot the rule locus. Okay? So here, section 1 is once again, the open loop transfer function only has real axis poles and real axis zeros. Section 2 is for open loop transfer function that has complex poles and complex zeros. Due to the limit of time, we only take care of the section 1. Okay. Section 2 leave for you to exercise if you want, and the exam only cover the section 1 scenario 2. Okay. Once again, exam 3 will only cover the section 1 scenario, where the open loop transfer function only has real poles and real zeros. Is it clear, first of all? Any questions regarding this handout, how to read this handout? All right, so let's move on here. So section 1, if the open loop transfer function only has real poles and real zeros, how to deal with this? First, there are some properties here. First, the number of branches of the locus equals to the number of closed loop poles. Why so? Anyone can understand this? Why so? It's actually very easy, right? How many branches you have? It's all up to how many closed loop poles. Because root locus is the path of closed loop poles. If you have only one closed loop poles, then you should have just one branch of the root locus. One branch means it's starting from somewhere, ending by somewhere, which is this one branch, right? Only one pole. With the increase of the k value, this pole move along this path, right? Only one branch. So the number of branches equals to number of closed loop poles. Second, the root locus is symmetrical about the real axis. How this makes sense then? It's symmetrical about the real axis, okay, not the imaginary axis. X-axis is the real axis. It's symmetrical about it. Why is that? Well, you can imagine you have poles along the real axis, right? And you might have conjugates, complex poles, right? All of these are symmetrical about the real axis. Does it make sense? All of these poles, okay, no matter what, they're definitely going to be symmetrical about the real axis. Yep. Here, like Noah mentioned, the conjugate poles, the flip 180 degree, yeah, same meaning. So if your locus end up with something asymmetrical about the real axis, then definitely wrong. That's not possible. No matter how complicated the system is, the result of the root locus is definitely symmetrical about the real axis, because the poles is definitely symmetrical about the real axis. No otherwise. A third is saying the root locus begins at open loop poles and ends at the open loop zero. This is a very important first step. Okay, this is very, very important. The first step for us to sketch the root locus. Okay, and the number 4, the number of the open loop poles equals to number of open loop zeros. Why so then? This is because back to number 3 here. Okay, we just mentioned root locus consists of multiple branches. Each branch begins at what? Open loop poles and ends at open loop zeros. So open loop pole is the starting point, open loop zero is the ending point. The number of open loop poles equals to number of open loop zeros. That makes perfect sense, because once you have starting point, you must have an ending point. Does it make sense? That consists of one branch, right? There's no case like you have starting point without an ending point. That's not possible. However, the ending point might be infinity. Okay, don't take me wrong. The ending point might be infinity. That's possible. but still that is ending point. Okay, so your number of starting point equals to number of ending point. Okay, this is how you understand it. And then next is really start to sketch. So on the real axis, the real locus exists to the left of an odd number of real open loop poles and open loop zeros. Well, without a real exercise, an example, we won't be truly understand what this number 5 is talking about. Okay, so let's have a example. Let me split the screen in this way. And sketch the locus of following system. All right. So to sketch the locus, obviously the first step is to have the open loop transfer function, right? First step is very straightforward. You're introducing again K here, that's okay. But the open loop transfer function must be clear, KGH, right? This is the open loop transfer function. Next, we need to look at our handout and saying number 3 is saying if the locus begins at open loop poles and ends at open loop zeros. So obviously you need to understand who are the open loop poles and who are the open loop zeros, right? Who are the open loop poles? This is very straightforward, right? Who are the open loop poles according to this? Who are they? Anyone can tell? 0, -1, and -2. Here we go. Okay, as Kevin said. Okay, that's it. That's it. 3 open loop poles. And who are the open loop zeros? This becomes tricky. And no, if 0 is 0, if the 0 is 0, that means what? You have a S in the numerator. Does it make sense? Let's be very careful. Okay, 0, 0 means you have S term in the numerator. However, we don't. Okay. So actually, the 2 and not answer make more sense. And they're saying, well, none. Actually, none. Yes, truly none. However, you need to read here. The number 4 is saying the number of open loop poles equals to the number of open loop zeros. And we know we have 3 open loop poles. Therefore, what? We must have 3 open loop zeros. And who are they? This is a little bit tricky. Once again, open loop poles are starting point. Okay, remember this. And open loop zeros are ending points. Ending point are where? This is, as I said, this is a little bit tricky. First, you must match the number. You match the number 3. You must match the number 3. The second, infinity as the ending point. That's okay. That's obviously makes sense. Okay? That's not something terrible. Okay? You're starting somewhere, we can identify by the open loop poles, and they are ending somewhere we cannot see anymore. That's okay. Infinity. So we are saying open loop zeros are infinity, infinity, and infinity. 3. The number must be matching. It must be matching. So here is a little bit tricky. Yes, yeah, a little bit tricky. Move on. Move on. After finding this, next we try to follow number 5. Number 5, which is along the real axis, or say on the real axis, the rule locus exists to somewhere. And obviously, what we want to do is locate all open loop poles and zeros. Poles and zeros. What does it mean by locate them? You just label them, right? Just label them. Let's assume we have a S-plane, right? So label all of the open loop poles and open loop zeros into the picture. Open loop zeros are 3 infinity. We don't need to do this, right? We don't need to do anything about them. However, open loop poles, we need to label them. 0, 91, and 92. 0 poles, okay. They're poles, not zeros. So the symbol is what? Cross. 0, -1, and then -2. 3 zeros represented by 3 crosses. And then go back to number 5. It is saying along the real axis, the rule locus exists to the left of an odd number of real open loop poles and real open loop zeros. What it means is this: you're counting from right. You're counting the number of them. Listen carefully. You're counting the number of them from the right. Okay, therefore the first one you come across is open loop post 0. The number is what? 1, right? 1 is odd number. So the rule locus exists to the left of 0. Okay, so we do have rule locus left to pole 0. Because this is the first pole, and the first is odd number. Keep counting. We passed -1, and then how many we have now? 1, 2. 1, 2. 2 is an even number, not odd number. So nothing exists to the left of 91, right? Nothing here. Keep counting towards left. We're coming across the third open loop post 92. So how many? 1, 2, 3. 3 is odd number. So rule locus exists to the left of it. So we're counting numbers rather than the values of the poles. Okay, we don't care about values. Values only matter where we place those poles or zeros. When we plot the rule locus along the real axis, what matters is the number of them. Okay, we count from the right. Okay, we come across the first one, so the left to it, okay, because first one, number 1, is odd number. Passing 91 here, there's nothing here because 1, 2. 2 is not odd number. Further past 92 here. Here we have 1, 2, 3 is odd number. in this particular example, we only have open loop poles. However, be careful. Open loop zeros also count. Open loop zeros also count. In other words, if you're counting one open loop poles and the two open loop zeros, they all count. All right, so this is how we plot the rule locus along the real axis, real axis. Okay. So we basically done number 5. Move on to number 6 on the handout. By the way, any questions? All right, if this is fine, we move on to number 6 here. We start to take care of the outside of the real axis. What does it mean by outside real axis? It means this, right? Now we have rule locus along the real axis, or on the real axis. Do we have anything here? Here, right? So first of all, you need to judge, do we have any outside real axis? Okay, you need to judge this. You need to answer this question. How to answer this question? Or just to this particular example 4. Here, do we have outside real axis rule locus, and why? Anyone can tell? Or any thoughts? Speak. Sawyer said we do not have outside real axis rule locus. Any other thoughts? And why so then, Sawyer?
We don't have any zeros, or we don't have any poles that have imaginary parts.
That's right. So we won't place them into the this S plane. So that's all. However, be very careful. How to answer this first question? Do we have any outside real axis? It's not depending on where we placing our closed loop, where the open loop poles and zeros. It depending on what? Depending on this. Look at this part, this branch. This obviously we are seeing 2 branches. Okay. So to this branch, what we are seeing? We have one starting point, which obviously is the open loop poles -2. Starting point, no problem. Do we have ending point? We do. Okay, no problem. Ending point is what? One of our infinity. Right? So what do we say? We say we have a complete branch starting from -2 all the way to infinity. It's a complete branch. No problem. This branch is okay. We don't need to worry about it. However, look at this second branch. What do you see? 2 open loop poles, right? And never forget, open loop poles are what? Are starting point. And they only be starting point. What does it mean? It means this rule locus branch, there's one rule locus branch starting from 91 towards right. There's another branch starting from 0 towards left. Does it make some sense? Because both are starting points. Okay, we can't violate this property. It's not like this, because this is one starting point 92 and towards left. Okay, Infinity is the ending point, is receiving this the end of the branch, Locus branch. So it's okay. This is obviously not, right? Both are starting point without seeing any ending points yet. Okay. Hold on 1 second. All right, so here, let's move on. Any questions regarding this consideration? So based on this discussion, you should be able to tell, actually, we do have to have outside real axis rule locus, because we have actually this part contains two different branches. Does it make sense? So also they correspond to infinity ending points, yeah, because these are two starting points. Where are their ending points respectively? Infinity and infinity. And then what matter is 6b. 6b. If so, or if we do have outside real axis rule locus, what we need to do is find the what is this? Asymptote. Asymptote. You guys probably learn or have done something related to asymptote in math class, but here we are using asymptote to help sketch the rule locus. Okay. How to find asymptote? Okay, and first of all, asymptote is not part of the rule locus. Okay? Be very clear on this. Asymptote is not part of the rule locus. Okay. So how to find the asymptote? You have two things to figure out. First thing is, because the asymptote is straight line, it's straight line. So what you need is two things. One is slope, or say the angle with the real positive real axis. Second thing you need is one point, right? Or say one intersection point with the real axis. Does it make sense? These two things can determine one straight line, which is the asymptote. That's why we are taking care of them respectively. First, intersection point with the real axis. How to find this point? Once again, intersection point with the real axis. Okay. So how to find that point? Is equals to a ratio. A ratio in the numerator is the sum of finite poles minus sum of finite zeros. Denominator is number of finite poles minus the number of finite zeros. Let's see our specific example, how to find these numbers. Intersection point equals to a ratio. Numerator is the sum of finite poles minus the sum of finite zeros. Okay. Denominator is number of finite poles minus number of finite zeros. So let's take care of the denominator first. The number of finite poles is equals to what? Here. What is it?
3.
3, right? There's 3. Yep. Minus the number of finite zeros, which is what?
0.
0. Here we go. So 3 minus 0 is the denominator. Numerator is the sum of the value, not the number anymore. It's the sum of the value. Sum of the finite poles. Does it make sense? Minus the sum of finite zeros. We don't have any. It's just a 0. We don't have any finite zeros, right? So this is the intersection point. Once again, this is the intersection point between the asymptote and real axis, which is 91, okay? 91. This is the intersection point. Okay. Second thing we need to plot this asymptote is the angle. Right? The angle. How to find this angle? The equation is given here. The equation is given here. Let's see how to do this equation. So it is equal to a ratio as well, and the numerator is 2k plus 1 pi. Okay, it's an odd number times of pi, right? It's okay. The denominator is the number of finite poles minus the number of finite zeros. This is a copy previous here, right? It's copying this. Both denominators are same. So this angle is what? Here we need to assume a little bit. We assume maybe 1 or 2 k values. For example, if k equals to 0 or k equals to 1. Let's see. If k equals 0, what is the angle value? Power 3, right? If k equals to 1, then what is the phase angle value then? Pi. Exactly. Pi. Right? You can try more, okay? You can try more. But you're going to be able to end up with negative pi over 3. Be negative pi. 0. Okay. Let's just utilize these values. To plot the asymptote. Once again, asymptote. Okay, it's not part of the rule locus. So according to this, how to plot the asymptote? Intersection point 91 here. Angle of pi over 3. What does it look like? Does it make sense? To be differentiated from the rule locus, we'd better use dashed line. Does it make sense? The dashed line makes more sense, actually. Not part of the rule locus, the dashed line. Pi is what? The pi or positive or negative pi is just the real axis. We don't need to worry about it. And how about negative pi over 3? Negative pi over 3 is here. So here is over 3. Here is negative pi over 3, right? Of course, it makes perfect sense. Remember, the rule locus is symmetrical about real axis. Therefore, so should the asymptote. Does that make sense? So these two values makes perfect sense. Pi and negative pi, well, they're not quite helpful. So this is how we find the asymptote. Okay, how we find asymptote. Okay. All right. Be careful. Still enter the roof of outside real axis rule locus. Okay, still enter this roof. After finding the asymptote, we need to find what? Find this. Okay, what is called? Called break in or break out point. What does it mean? So the rule locus go along with asymptote based on the break away point or break in point. What does this mean? Look at our rule locus now. We're expecting to see the branch out of this region, get out. and then to move along the asymptote, right? That's what does by asymptote. You need to have a curve moving towards it, trying to be aligned with it. Right? However, you need a point to break out, right? To break away. Here, the definition is called breakaway point. You need point to break away or break in. Of course, in this particular example, it's breakaway point, right? It's not break in point. Why?
You're already on the real axis, so where are you going to go from breaking in?
Well, that's not exactly the reason, because if you imagine if you some point, if you go into here, that's possible. Let's break in then. So it's not up to that, actually. It's absolutely possible to be break-in point along the real axis. Right? It's up to something else. What is it? Any other thoughts? Why it has to be break away for this particular example? Why? Any idea? Here, Kevin's saying is direction of rule locus. I think that's basically the correct answer. But never forget, we are talking about a rule locus between two starting points, right? What does it mean by starting points? They are both open loop poles, so they are moving the rule locus towards one point and then leaving. Does it make sense? Because the direction of the two poles, two branches. This is one branch. This is another branch. They're both converging into one point, and this point after converging together, after merging together, they can leave the real axis, leaving, right? So a waypoint rather than in point, break in point. That's the reason. In other words, imagine another scenario in where we have two zeros. Okay, zeros are represented by circles. And if we do have rule locus in between, due to two open loop zeros, what's the direction of the rule locus? This way, right? Because these two are ending points. They cannot be starting points. They can only be ending points. So outside rule locus gonna what? Break in, right? Does it make sense? Only break in. Otherwise, it won't make no sense. This is only be break away. Is that clear now? Any questions here? Okay, this is why it must be break away point. I mean, for this particular example, yes, it must be break away point. And what matter next is where to break away, right? Where along this part, along this section, where to break away, right? That's why you need to find this breakaway point by this equation here. By this equation here. And I think I can stop here and continue by next lecture to finalize this rule locus plotting and go through maybe one more example. All right, thank you for attending today's lecture. It's a quite a bit quiet lecture today. I don't know why, what's going on, you guys, but hopefully everything is clear. And talk to you guys on Wednesday then. All right, thank you. Bye-bye.